Good? Ah, yeah. Sounds turned on. So let's get started. Yeah, I'm starting a bit earlier, which means I can talk a bit longer, I hope. This talk that I'm giving, I've given it at a couple of other open source conferences. I tend to change the slides every time I give this talk, so it's sort of seeing whether this time it will be going as good as the previous times I gave this. It's really experimental. So yes, my name's Schouten. I'll give a short introduction about myself. Since 2008, I'm a developer at the FreeBSD project. Who of you guys know FreeBSD, the operating system? Oh, a couple of people. So FreeBSD is a Unix-like operating system. It's similar to Linux. It's not the same as Linux. Back in 2007, I started contributing to it. I started using it, and I was one of the first people who ran it on a Microsoft Xbox at the time, the old game computer. As a result of that, I got my SVN access at the project and started sending in patches regularly. In 2009, the FreeBSD project was investigating whether it should switch over to Clang, LVM Clang, the new C++ compiler that's also shipped with macOS nowadays. I was one of the first people who was really actively working on getting it to work on FreeBSD properly and fixing bugs in the FreeBSD code that prevented it from building with LVM. So in 2009, I also gained SVN access at LVM, so I also still send them some patches now and then. I'm not that active at the LVM project, but you'll see in half an hour how sort of my work that I'm doing right now relates to LVM. Between 2012 and 2014, right after I graduated, I moved to Germany, worked there for a couple of years. And as of 2014, early 2015, I have my own small consulting company where I do some freelancing work, and I'm working on the work that I'm about to show you today. So the structure of this talk is that instead of immediately focusing on what Cloudabi is, as you saw on the title slide, I first sort of want to explain sort of the problems it's trying to solve, sort of the sentiment behind it, why I started working on this specific project. So I've been using Unix-like operating systems for about a decade, and what I've noticed is that they do a really poor job at stimulating people who write software to actually design applications that are reusable, and I'll explain later what that means, testable, and at the same time I'll also explain what that means, and secure. So first starting off explaining why I don't think that Unix sort of makes it easy to make reusable and testable programs. Let's first sort of step away from operating systems and first talk about reusability and testability at the software level. If you're designing applications, you're writing code in a higher level programming language, it could be C#, it could be C++, it could be Java, Python, it doesn't really matter. Around the year 2000, a person called Robert Martin, better known as Uncle Bob within the sort of object-oriented programming community, who's also one of the authors of the Agile Manifesto, wrote a document where he came up with something called the solid principles. And the solid principles is sort of 5 rules, and if you sort of stick to those 5 rules, you end up writing software that typically tends to be of good quality. And one of those letters of solid, the D, stands for the so-called dependency inversion principle. And basically what it means is if you're designing an application, don't hard code it to make use of certain things that it depends on. Make those things configurable, make it possible to inject those. So if you've ever heard the term dependency injection, that's sort of related, or that's a way of accomplishing the dependency inversion principle. So here I've got a couple of slides where I'm giving sort of a piece of Java code that really explains what dependency injection is. So consider you're writing a really simple web application, for example in Java, a simple class called myWebApp. And this myWebApp class probably has some kind of function where it gets called every time an incoming request is being processed by the web server, and your class sort of has to handle that request, come up with a sane response, some HTML code, and print that back to the client that's connected. So one sort of ugly way of implementing this class is sort of what I'm showing you here on the slide. This web application apparently depends on a MySQL connection. So inside of the class, we store a MySQL connection member called DB. And when we're constructing this class, we sort of construct a connection, a MySQL connection probably coming from some kind of MySQL client library that connects to our database server. And in this case, it's called foo.com, but it will likely have a different name. So the downside of implementing this class in this way is that the server that you're connecting to is completely hard-coded in this class, of course. So say if you both have a production and a staging setup, then this approach won't work, of course. So you can improve this class by writing this code as follows, where instead of passing in a string containing instead of always making use of foo.com, you add a parameter to the constructor where you say, this is the host name I want to connect to. This is actually what most code looks like, but many people who write object-oriented software would agree with me that the best way of writing this class is like this. So on the previous slide, one of the downsides that was still present in the code was that it made like a strong use of MySQL. So in practice, it might be the case that you want to move this site over to a different hosting provider that doesn't make use of MySQL, but uses some different system. It was recently announced that Microsoft SQL Server was also available for Linux nowadays, so maybe people want to use that as well. So yeah, then instead of using a MySQL connection, you just want to use some kind of interface called a DB connection. And it could either be a MySQL connection object or a Postgres connection object, or it doesn't really matter. And this is actually sort of the flexibility that you want. It also makes sure that you don't sort of get this growth on all sorts of logic that ends up in the class. Because take a look at the previous class that you had over here. Say if you wanted to use custom credentials to connect to the database server, or a custom SSL certificate chain. Well, if you keep on adding all these arguments to the constructor, at the end you end up with a constructor that takes 20 arguments, whereas with this piece of code that I gave over here allows you to create like any database object that you prefer and pass it into the class, which is like a lot cleaner. So this makes the code a lot more reusable, but now looking at the testing aspect, what's also really nice about this approach that I gave on the previous slide is that you can also, in Java, write your own fake database connection. So in case you want to test this page, for example, it's, I don't know, a news page where you have a couple of news items that need to be returned. What you can do is create this fake class where you say, like, if the query equals select star from latest news items entries, then return these fake fixed headlines. And then you can create this really simple unit test where you check that the output that you're getting corresponds to what you would expect. So from a testing point of view, this is also like the way you want to write code, by injecting your dependencies instead of hard coding their dependency. So a couple of years ago, I started noticing that Unix is a bit like the first two pieces of code that I gave. So in sort of in the area of software development, we really want to use dependency injection, but Unix apparently doesn't use it at all. You have an application where, for example, take your Apache server, you start it up, it automatically assumes a lot of things that it needs to do. It has built-in options that determine how this program should behave. And some of those things can be altered by specifying how it should behave in a config file. But what you often see is that this config file is also stored at a hard-coded location, and trying to override that also takes a whole bunch of command line switches to get that to work. Some things you can't even override. So a very good example is, say if I wanted to start up a second web browser on my laptop, for example, but I want to let only that instance of the web browser use a different DNS server, because I just want to test, somebody's complaining about a DNS server not working. I just want to use a custom DNS server in this single instance of the browser. That's, as far as I know, practically impossible. There's no easy way to say to an application, like, all the applications on the system, they need to read the DNS servers from edcresolve.conf, except this single application. It needs to use different DNS servers. And this, in my opinion, this really limits the way people can use software on their computers. So here on the slide, I'm giving two other sort of downsides of the approach that Unix is taking. First of all, yeah, you can't run the same process twice. I mean, there are many services that, already on startup want to write process ID files in the same directory in var run, or they want to bind to the same IP address or and port number, or they want to create a Unix socket in the same location. That really prevents you from starting up an application twice, even though you could be interested in doing that. For example, if you want to start the application for multiple customers that both have sort of a separated environment. The second problem is you can't also reproduce an environment. Applications, they make use of so many files stored on random locations on disk. If you want to start up an application in such a way that it behaves exactly like the previous instantiation of it, then it's almost impossible because the entire environment could have changed around it. So far we're adding all these workarounds to actually deal with this. So I remember back in 2003, 2004, the first time I went to the FOSDEM conference in Brussels, there was this huge hype around Xen. Virtual machines were suddenly like, suddenly not so slow anymore that people would actually want to use them in production. A couple years later, KVM became really big in combination with QEMU to emulate complete pieces of hardware, and just so you could run Linux multiple times on the same physical server. Nowadays, you see that there's sort of a shift more towards what I would like to call namespace trickery, where people use containers where you can create sort of separate namespaces in which you can run all these processes. So then you can actually start up a process multiple times, simply by running it in a container, for example. But in my opinion, those approaches are not tackling the underlying problem. They're only just sort of, workarounds to it. We know that Unix is badly designed, and we're sort of solving it by, putting tinfoil around all of our programs, we're really boxing it up, and, we're not actually making the applications nicer in that regard. We've just given up on that entirely, and we're just patching up the operating system to make it less hard for us. But in my opinion, those solutions have the problem that they reduce the transparency significantly. If apps are running in a container, they're more annoying to debug. There are more things that you need to take into account. For example, if you're running PS inside of a container, it's not the same as running PS outside of the container. Process numbers that you see outside of the container are different from process numbers that you see inside of the container. And all of those sort of subtle things, they add more barriers towards making it easy to debug your application. So this is all I'd like to say about testing and reusing for now. This being a security conference, let's focus on sort of a more interesting part. Assume you sort of have a traditional Linux server on which you're running a bunch of processes. So assume you're running like Apache or Nginx to serve some web pages. You're running postfix to receive incoming mail. Just go on. Just think of a couple of services. And on that server, you can run PSAUX to get a list of all the processes that are running on the server. And just as a thought experiment, for all of those processes that are running on your system, think of what they need to do as part of their operation, and think of what they are allowed to do as sort of what Linux allows it to do. So, for example, web server is really easy. It only needs to accept incoming TCP connections on a socket that it's already bound to on startup. It needs to process some requests, maybe send it on to like a PHP process that opens a single file on disk containing some PHP code, runs it, and then returns some kind of response. It's all fairly simple. But if you then sort of start to think about what it's actually allowed to do, taking a look at the entire list of system calls that Linux provides, think about the things that it can actually access. Take a look at /proc, the procfs directory, and just all of the files that are in there and sort of the vast amount of information that it can actually extract. Even if you're not root on a Linux system, there's actually quite a lot of data, interesting data that you can extract from the system. So this is sort of like the drawing that I think of when I think about this problem. Like on one hand, I'm sort of thinking of it as sort of a one-dimensional problem. Like on one side of the spectrum, you're in a situation where you're not allowed to do anything. You're a process, and the only thing you can do is, I don't know, add some numbers together, do some arithmetic, and allocate some memory, and that's it. And on the far end of the spectrum, you're user root, and you can do anything. You can send raw Ethernet data. You can read all of the individual bytes on the hard disk. And ideally, when you start a program, like a simple web server, it only needs to do like a very small number of things that the operating system provides. But in practice, the amount of things that it can do, that the operating system allows you to do, is actually fairly large, even if it's not running as user root. So, about a decade ago, people in the Linux community, they started to realize that this is actually quite an annoying problem. So, what Linux did is they added a framework to the kernel called Linux Security Models, LSM. And LSM is sort of an extension to the traditional Unix permission model, where they've added all sorts of hooks to interesting places in the kernel where you'd like to add more complex authentication. And you can write your own kernel module to add a policy to this. And there are two kernel modules that are used sort of most often, that are like the biggest user of Linux security models, and those are AppArmor and SE-Linux. So with AppArmor and SE-Linux, what you do is you sort of write an additional policy file that explains, like, this is an Apache process, and this program only needs to access these exact files on disk. The problem with this model is that the security policy that you're using, what actually needs to be part of the security policy, depends on how the application is configured. So for example, depending on which modules you're loading in your web server, Apache is like a modular system where you can load additional shared objects to make it more functional. That really influences the security policy. And because of that, it's also really impossible for Linux distributions to, out of the box, offer a security policy that actually works. It has to be really broad, because users are able to configure the web server in any way they like. They can configure it to read files from arbitrary paths on disk. So the security policy that they ship must be really broad for it to work, because otherwise what you see is that people can't get their version of Apache with their configuration to work on their system, so they end up disabling AppArmor, which is even worse. So what you see is that to get a security policy that's actually sort of like a tight fit for the program that you have, is that you make use of something called learning mode. So you start up Apache, and you let it run for a couple of days, or a month, or some arbitrary amount of time, and it logs all of the actions that that Apache is performing. So after those 2 days, you get a huge list of all the system calls that it ran, and that can be used as the basis for your security policy. But the problem with this solution is, how do you know that you've actually run long enough to actually have a complete policy? Are you sure that during that, for example, 1 week time frame, you got all of the different HTTP requests on your web server that actually exploited all of the functionality that your web server has? That's really impossible. So what I've noticed in practice is that having a policy that's too strict, so a policy that actually doesn't contain certain rules that are needed to make this program work correctly, can be very dangerous. Even if your application starts up and seems to work properly, you start up your Apache with your custom security policy, and you go to a couple of pages, press F5, and it works, that's really not enough. Even if you think if it works, it doesn't necessarily mean that it runs correctly. One of the worst things I've discovered is that if OpenSSL, the commonly used crypto library, cannot access dev random, then it falls back to using this really unsafe entropy. It only gets the time of day and the process identifier of your process, and uses that as the initial randomizer state. So it also doesn't give you any warning about it. So without any notice to the user, it actually uses unsafe cryptography. So you try to make your application more secure by using AppArmor, and in practice you actually made it more dangerous to use. So I'm actually a believer that writing security policies is a complete waste of time. And any security framework for Linux or for Unix systems in general, that tries to add more security by adding security policies is, in my opinion, just useless. You shouldn't use this. The point is, what an application should be allowed to access is already encoded in the design of the application. And especially if you're using principles like dependency injection, what your program depends on actually becomes really obvious. So taking a look at the pieces of Java code that I gave before, this is the first example that I gave, and I've sort of grayed out some parts of the code that we don't really need. If you're just looking at the outside of this class, so you would generate documentation out of this, or really only look at the API, then it's impossible for you to know as an outsider what the dependencies of this class are. But now if you look at the version that makes use of dependency injection, it actually becomes really obvious. You know that it's going to make a connection to a database server. So this brings me now to the part where I'm going to explain what Cloudabi is, and I can be really brief about this. Namely, it's sort of a flavor of Unix. Well, flavor of Unix. It's a runtime environment for Unix-like systems where you have to use dependency injection. So you have to think of this as sort of a separate development environment. So you have a separate C, C++ compiler that you use to build special Cloudabi programs. And those programs can be started on several operating systems, so you can run them on Linux, for example. And those applications, they are all written in such a way that all of the dependencies are injected. All of the APIs that conflict with this model, so being able to open arbitrary files by giving an arbitrary path name, being able to create a TCP socket to create like a random outgoing TCP connection to some destination on the network, all of that stuff is removed. The only things that remain are functions that operate on like local objects, file descriptors. And the nice thing about Cloudabi is that it's sort of secure by default. So if you would write sort of the simplest possible Cloudabi application that you could think of, then the only thing it can do is just compute some stuff, allocate memory, and do nothing else. Meaning that it's even safe to start up an application that you completely don't trust, in theory. I mean, there could be exploits, bugs in my implementation, but according to the design of this system, you can even run programs directly on top of a Linux kernel that you don't trust. You don't need to use special virtual machines for this purpose anymore. And as soon as you want to sort of add functionality to this program, being able to connect to communicate with the outside world, you inject dependencies. And sort of a practical example of how you'd use this environment is like the following. Assume you want to write a very simple gzipping program, a simple compression utility. The only thing it needs to do is read in stuff from a single file in uncompressed form and then write out the compressed representation of that file to some other file descriptor. With Cloudabi, you would really just model it as a simple application that starts up with 2 file descriptors. For example, 2 pipes, 2 files, 2 sockets, doesn't really matter. And you could implement it as a simple tool that reads stuff from one file descriptor and writes it out to the other. So with this model, software is also reusable and testable by default, because programs can't just have any global state. They can't, make random outgoing connections. You can really override the entire view of the outside world that it has. So, for example, with that web application that I showed before, where you have a separate production and a separate staging environment, you can be 100% sure that if you want to run this web server in your staging environment, that it won't accidentally use your production database, because it doesn't even have a notion of how to connect to the production database. So now I've come to the part. I had a couple of slides where I sort of show how Cloudabi works. I only had those here in my slide deck in case demos would fail, but now I'm going to sort of switch over to my terminal and sort of explain how you could use Cloudabi to develop programs and actually run them. So here on my desktop, I've got a demo folder, but here I'm going to go into it here in this terminal. Oh, yes. So yeah, the font size is big enough. I guess all of you can sort of see what I have on my terminal. What I've done is I've built a very simple web server. A large part of the C code you can actually find in the documentation of Cloudabi, but it's a C file that's 65 lines big, and it implements sort of a very stupid web server that's probably not compliant to any HTTP specification, but it's sort of good enough for this demo. Before I'm going to look at the top of the file, let's just look at the bottom of the file, because that's actually sort of where the most interesting things happen. So what you see here at the top of this source file is that, or this piece of code is a loop, and what it does, it sort of accepts incoming TCP connections, and it writes a fixed response to it. So what you see here with this piece of code that I'm highlighting right now is that it's writing a HTTP response across the socket and then closing the connection. I'm not attempting to do any sort of processing of incoming HTTP requests. I'm only writing out a fixed response, so that's pretty bad. So this is sort of standard C code that you could also just compile on a standard Linux, Unix system, and it should probably just work. But where the interesting part is with Cloudabi is here sort of at the top of this source file. And this is actually where I'm dealing with the dependencies that are being injected into the application. So normally a traditional Unix web server would have some startup code there saying like, create a socket, bind it to a TCP port, and run the listen function on it so that it will start to receive incoming TCP connections. What I'm doing right now here with this piece of code in this block, on which I'm clicking right now, I'm extracting file descriptors that are being passed in through a configuration file. So if you want to start up a Cloudabi program, you sort of have to write a configuration file where you explain sort of as a replacement for traditional command line arguments that you normally have on Unix, and as a replacement for configuration files that are normally stored in /edc, you have to specify all of the configuration attributes and all of the resources on which your application depends. So that's what I'm doing in this loop, and in a couple of minutes you will see what the configuration file looks like. So I'm first going to show you how I can run this web server, and then later on we're going to take a look at the configuration that I used to start this up. So there's a very simple utility called cloudabi-run, and it can be used to start up a Cloudabi program together with its configuration file using this syntax. So you just say cloudabi-run space executable, and then on standard in, you pass in the configuration file that needs to be used. So now what's this? Oh, wait, sorry. I need to specify an additional command line flag. I'll explain more about this later during the talk. But now I've got my web server running. So now I'm going to fire up a browser. And here the screen is quite filled, the resolution is pretty low. And now if I go to localhost :12345, you actually see that I'm serving this response that, this sort of fixed response that I had encoded in the source code. So here I can just refresh it a couple of times and you see that it actually prints some log entries out to standard out. So now I'm going to show what the configuration looks like that I used to run this. Yes, here it fits all on screen. One of the things that I discovered while I started working on this project was that YAML, the YAML language for, that you can easily use for configuration files like this, is actually a typed language. So it can not only be used to sort of store simple strings and integers and booleans and floating point values and lists. You can actually create your own types in this language. And YAML calls this tags, and this is a feature that I'm using a lot for Cloudabi to actually sort of make this work. So here what you see is instead, like this is the configuration that's being passed over to the application, but I'm using special tags where I can sort of specify resources that need to be passed onto the application. So what happens, Cloudabi run parses this configuration file, it looks for all of these tags, things that start with an exclamation mark, and it actually processes these special tags. So in the case of this socket tag that I have over here, it actually gets replaced by a file descriptor of a socket. So this pre-processing pass that Cloudabi run has replaces it by this. So it opens the socket for you and puts the file descriptor in its place. The same happens to like the log file directive, where I say that log entries need to go out to standard out. It also replaces this by a new unique file descriptor number. You could also have some other things in here. So, for example, if I would want to have a certain directory where I have to store HTML files or PHP files, I could, for example, add an additional key to this, like www.root:/file path var blah, 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 something like this. And what happens is that Cloudabi run just runs over this and replaces it by yet another file descriptor. And what Cloudabi run does is it makes sure that only the file descriptors that are specified in this configuration file end up going to the application. So all of the other file descriptors that happen to be open are all closed. They're not accessible to the program. So if I would run the program like this without log file, then it can't even access the terminal because it doesn't have a file descriptor to the terminal. So it's a really file descriptor-centric system. So let me close this. So with Cloudabi, when I started implementing this, this was all mainly developed for C, C++ code. So when I started off, I took a version of, I took the Clang source code, LVM source code, and I ported it over to Cloudabi so that you could use Clang to compile stuff for Cloudabi. So you can just compile a simple application like this by saying like, using the cross compiler, run the cross compiler with -o saying where the executable needs to be stored, and then you pass in the source files and it builds. So after I've got C and C++ working, I decided to also focus a bit more on other programming languages. So for example, after I gave my talk at 32C3 last year in Hamburg, one of the people in the audience was also really interested in having Python ported over. So there is also a port of Python where here I'm running a very simple Python script, which I can show you as well. Oh, here. So this is a configuration that can be used to start up Python and run a simple script. So here at the bottom, you actually see like the script that needs to be executed by Python, which we pass in through like a variable in our YAML file. And here at the top, you can see that we're passing in a file descriptor to a directory containing all of the modules that Python is allowed to load during its runtime. Python is not just a single executable on its own that can run all of these scripts. It actually depends on its environment or like a directory on the system that contains a whole bunch of loadable modules and Python scripts that implement all of the logic. So if in your Python code you're saying something like import math, where you have like a sine function, cosine function, all mathematical functions, that's all done through like a Python file that's stored somewhere on disk. And in this case, it's stored in this directory. You actually see that you have to pass this into Python to actually make it work. And what you see over here with this Python script that we have, it can also depend on some other things from its environment. So for example, we want this Python script to just print like a simple hello world. We also want to provide some arguments here that are passed on to the Python script. So here, if I run the script, you actually see that it only prints like hello Antoni Gaudi, and you see that this is just composed from like here. This is the format string, but it fetches these arguments from like the argument section in the YAML file. So first name, last name, they are all stored under name sys.argdata, and they can be pushed in here. And the same also for the terminal. So you see that there's an output key over here, which gets turned into like a stream over here on these lines. And here we can use s.write to actually write a piece of text over this stream. So you can also use this approach in Python to create web services as well. I showed a web server written in C, but you can also write a web server in Python. I've got a good article about that on my blog. I'll show the end the link at the end of my talk. But if you're interested in doing Python programming, then do check this out. I mean, it can already be used to run a lot more interesting Python scripts than what I'm showing over here. So going back to the slides, here, this is, the previous slides were sort of replacements for the demo. So, So one of the nice aspects of Cloudabi is that it's also a cross-platform system. So you saw that I used a special cross-compiler on my Mac and actually just ran it on top of macOS. The programs that you generate using this cross-compiler, they're the same, irrelevant of whether you're on Linux or FreeBSD or on macOS. You just compile it once, you always get the same executable. Cloudabi-run just makes sure that it can be run on your operating system of choice, which is actually pretty cool because it means that you can now develop software on macOS, compile it on macOS, run it without a virtual machine. The performance is close to being native, being run natively, and then you can just copy it over to your Linux system and run it there. The ports for Linux, FreeBSD, macOS, they're like fairly complete. You can actually use them on a daily basis, day-to-day basis, without any issues. There's also work on the way to get this ported over to NetBSD. That's far less robust than the other one, so that's why I was a bit hesitant to put it on the slides. And the idea behind Cloudabi is, for now, I really want to sort of strongly focus on using it for writing software that you can run on servers, web applications. That's also what I showed in the slides. I think that's sort of a really good use case for using this approach. But there are some other sort of environments in which a system like Cloudabi could really help to make systems more secure. So you often see that, we've seen earlier during one of the talks, I think yesterday, that one of the other speakers demonstrated a way of, running firmwares of, for example, wireless routers on directly on top of your Linux system, so you could, experiment with them and find exploits in them. Well, that sort of really demonstrates well what an embedded system nowadays is. It's just a Linux system with some extra in-house developed software, placed on top of this. In my opinion, a system like Cloudabi could also be used really well to secure those kinds of systems. So if you're building your own wireless router or your own firewall appliance or spam filtering appliance, a system like this could really be used to make those systems more secure as well. What's also really nice about Cloudabi is that we're trying to come up with a system where you actually get a really consistent experience developing software on all those different operating systems. So what we have is we have a collection of packages. Here I can show you the GitHub page, because that's... We have a set of packages that we're all cross-building for Cloudabi. So for example, if you're interested in doing video processing, then I think we already have like some video decoder libraries in here. Where is it? X265. So for example, like an H265 video decoder encoder library, all of this stuff is already available for Cloudabi. So what we do is this repository sort of contains descriptions of how these pieces of software need to be built for Cloudabi. So there's sort of a recipe that explains where the sources for this library can be downloaded, but also contains a bunch of patches that need to be applied to make it build. And what we do is we then package all of these libraries for a variety of operating systems. So we have an exporter where we export all of this software into Debian packages, meaning that you can just apt-get a special version of X265 for Cloudabi on a Debian system. But at the same time, you can also install it as a homebrew package on macOS. So Cloudabi doesn't have its own package manager or anything. You can just use your own system's package manager to manage all of the cross-compiled libraries. Well, with the state of Cloudabi, as I've mentioned before, it's already usable, it's already there. I really would sort of stimulate people to sort of give this a try. If you're interested in C, C++, or Python development, and you're thinking by yourself, I actually want to sort of see whether I can actually run my software in a really strongly sandboxed environment, and I actually want to see how well it behaves in an environment where you can't just access all sorts of random files on disk, but really have those injected. And this is sort of a really good proving ground for seeing how testable your applications are. So yeah, this is all I have to say about Cloudabi. Maybe one of you guys have any questions for me? Thanks. Yeah. Yeah. So this is so the name Cloud ABI. It's also interesting where this came from. That sort of answers your question. So one of the use cases that I sort of eventually foresee for Cloud ABI, but that's sort of, I'm too far away from that to sort of get it off the ground right now, is that a system like this could also be used as the basis for like a really strong cluster management system. Right now it's the case, I'm working with Docker also on a like daily, weekly basis, and what you see is there's like a whole sort of big stuff of unsolved things like key exchange. You have a web application, you have a database server, and you just want to like let them communicate securely with each other. So right now you still need to use SSL certificates, have some kind of signing authority, all that kind of like bullshit. But if you would have a system like this, you could actually abstract all of that stuff like completely away, where you sort of have like a graphical editor where you can sort of have a canvas and say like, I'm dragging a web application on top of this, and then I'm dropping a database server over here, and I'm just drawing an arrow between them, and press a play button on the top right, and it all starts it up. And it uses this dependency injection system to actually set up the connections for you. So applications, they don't need to know any host names, IP addresses, port numbers of their backends. It's really all done by, the cluster management system. And that's actually why it's named Cloud ABI. It's an incredibly stupid name, but I, had to think of something. But that's sort of the end goal I want to go to. Right now, I'm really more interested in getting like larger applications working on this. You have to start somewhere. But the end result that I'd like to see is that it's really focused towards having like a more automated cluster and getting rid of all this manual stuff that we need to do right now. Yeah. Sorry? Yeah, so how this works is I'll first sort of explain how it works on FreeBSD, because that gives the best insight in how it works, and then later on I'll explain how it works on Linux and macOS. So FreeBSD has this really nice abstraction in the kernel where you can sort of learn it about multiple binary formats. So Cloud ABI just uses ELF executables. The only difference about Cloud ABI is that somewhere in the header of the executable, instead of using like the number 0 on Linux or the number 4 on FreeBSD, sort of this identifier number, it has a custom number, number 17, saying this is a special Cloud ABI executable, and it should be run as if it's a Cloud ABI executable. FreeBSD, when it loads this executable, it sees that number, and then it sort of provides it a different set of system calls. So Cloud ABI has its own system call table that is like a very small subset of the Linux system call table. So Linux applications, they can typically run 300 or 400 different system calls. Cloud ABI only has like 50 or 60 of those. They're all a lot more fundamental than the ones that Linux provides. And all of those have been designed to sort of stick to this capability-based security model. So on FreeBSD, you can run these applications in a completely safe way. There's no translation layer in user space or something where, with some trickery or messing around with pointers or whatever, you can bypass it completely and, do your own thing on top of like a standard Linux kernel, a standard FreeBSD kernel. It's all safe. On Linux, it's a bit harder because Linux doesn't provide a layer like this. It's really like the entire like system call code path of entering the kernel when you run a system call to processing it like the Linux specific flavor. That's all sort of hard coded, all fixed. So I've got a patch set for the Linux kernel to run Cloud ABI processes. It's a bit unfortunate that like if you want to run them natively, then you sort of still need to run a patched up kernel. It would be really nice if I could ever get into a state where it ends up only being a loadable kernel module. There's still some kernel patches that I'd need to get upstreamed to get to that state. But that's like what I'm hoping for. And then what you need to do is only run like insmod on loading a kernel module, and then you can run these applications safely. On macOS, it's more annoying because I don't feel like patching up the macOS kernel or explaining to users like, if you want to use Cloud ABI, just compile a custom kernel in your Mac and reboot. That will never work. So what I did during my demo, and well, it's good that you've asked this question because I forgot to explain what that exactly did. I added the -e flag to Cloud ABI -1. And what happens is that it then sort of loads the application inside of Cloudabi-run and runs it from user space directly. So it's running on, it's just a regular macOS process running an ELF executable inside of it. So the environment on macOS is not safe, and right now I wouldn't advise it for like, real production purposes. But then on the other hand, like, I really hope that this is a system where people use their MacBook to do the prototyping and then, throw it over the fence and run it on Linux. Yeah.
So then there is a different syscall list for each system, or you're using the same syscall table for all the implementations?
Yes, exactly. The latter. I'm using a single system call table. So
you're doing syscall tracing in OS X for emulating the syscalls?
Sorry, what's that?
You are doing syscall tracing for checking which syscalls are running and then...
Yeah, so the question is like, how do I capture the system calls? Yeah. That's sort of interesting. Cloudabi, so now we're going really in depth, but I do want to answer your question because the answer to it is actually pretty awesome. Cloudabi always makes use of a VDSO. So there's a library that's being injected into the executable saying like, you want to run these system calls? Well, here are the functions that you need to run. So there is, if you go to GitHub, and then to Cloudabi, there's actually sort of this text file that we have over here, and this is sort of the official specification of what Cloudabi looks like. So here, really explaining like there are these system calls that have this name, and they have these arguments. And what we do is we process this text file in a lot of different ways. We have all sorts of processes that turn this into different sorts of files. And the ones that sort of, really sort of answer your question is like, we also generate VDSOs out of them. So here we really have a library, like a tiny shim, that sort of has a function for every different system call. And if you run the process on macOS, on FreeBSD, then it only ends up using the syscall instruction to jump into the FreeBSD kernel. But if you're running this on macOS, then you end up in the emulator, and there you have custom functions implementing the system calls and actually calling into macOS. So that's how this works. There's a lot of awful details, but in the end, it's pretty awesome.
Okay, thank you.
Any other questions? Okay, well, then I guess everyone was sort of flabbergasted about all of the low-level details. Oh, yeah, thanks.
Thank you, Mr. Schouten.